All right, let's continue with compactness. So we said, let's review. Compactness says that if you have a set of sentences and every finite subset of it is satisfiable, so has a model, then everything together has a model, right? So even though every finite subset may have a different model, we still, compactness tells us that the whole thing together has some other model. Of course, this is an if and only if, because if a big set is satisfiable, then all the subsets are also satisfiable by essentially the same model. So actually, the model that satisfies the whole thing satisfies all the finite subsets. But the hypothesis that every finite subset is satisfiable might not use that one. The proofness of compactness we're going to see in like a month at the end of the course once we prove completeness. So it's going to be a corollary of completeness. So we're not going to see the proof yet. We're going to see the proof for the case of sentential logic next week, but not the one for first order logic, which is a bit more complicated. Though we're going to see a lot of applications. So we're going to just assume the theorem is true and use it without proof for now, and then we'll see the proof later. Okay, so the first application, we're going to be proving that certain classes are not elementary. Okay, so you guys remember a class is elementary if there is a sentence such that a class of structures, right? This is for a class of structures. So the class of structures is elementary if there is a sentence such that those structures are exactly the models of that sentence. For instance, the class of groups that we saw in the video last time is a set of all the structures which model the conjunction of the three axioms of the group. So it's a one sentence that contains the three axioms of groups. So that's elementary. So most of classes in algebra are elementary. And again, we said that if you have a finite set of sentences, you can put the and between them and make one sentence. Okay, so being elementary is the same thing as saying there's a finite set of sentences such that you're the models of that. So let's do one example of a class that so let's show one example where we show that a class of structures is not elementary. So there's no first order sentence that axiomatizes it. And for it, we need to review one thing. So first, groups. So let's first review graphs. So a graph is a structure that contains one binary relation. So E is one binary relation. So the vocabulary is vocabulary has only one binary relation, and it satisfies only one axiom that says that if x is related to y, then y is related to x. And remember, this is the same thing as saying the pair x comma y belongs to E. Okay, so the graphs are usually represented. So the V, which is our universe, is our set of elements in this case. We usually represent it as points. So that's V. And then E represent edges. So they are connecting. So it's a binary relation between two things. It can be true or false about two elements, right? So and they are edges, and it doesn't matter which direction the line goes, because if one is connected to the other one is connected to the one. So some of the edges, some of the pairs of vertices are going to be connected, and some are not, right? So every time I draw an E means connected. Okay, so let's say, for instance, that here's our graph, right? So a bunch of vertices, which are the points, the domain, and E is a set of edges between them. So that's a graph. So essentially, the networks are represented by graphs, right? You have nodes, and they are connections between them. So that's a graph. So the study of graphs is super important in combinatorics and discrete mathematics, and in computer science a lot, of course, because of networks. So but the graph is nothing more than that, a bunch of points and some connections between them, and some of them are not connected by E. Okay, so there is an important notion, which is that of being connected. Okay, so for instance, in this graph up here, we can look at, let's say, this point and this point, and we say, well, those two are not connected because there is no path taking you from one to the other. Okay, so connected means that there is a path, and a path is just a finite. Just a path consists of a finite sequence of nodes that you can go from one to the other going through an edge. For instance, those two are connected, the blue ones are connected, and you can connect them through this edge, and that edge, right? And let's say, and this one are connected because you can take a path and you can go here, 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 here. There exists a path going from one to the other, such that there exist edges in between any of those. Okay, so okay, cool. So that's what it means for 2 points to be connected. And then we say that the graph is connected if any 2 points are connected. Okay, so this graph here is not connected because we saw already that this vertex and this vertex are not connected, right? And if you guys can see, I guess the graph is kind of divided in 2 parts. You guys can see that, like there is this part up here that is kind of separated from the rest, right? It's not connected to the rest. So the graph is not connected, right? So it wasn't connected. Those 2 parts are not touching each other. So this is the graph is called disconnected. Okay, so a connected graph is one where every 2 points are connected. Okay, so now the question is, let's consider the class of connected graphs. So this is a class of structures. And is that class elementary? So is there a sentence that you can write, and so that the models of that sentence are exactly the connected graphs? Well, the theorem is that no, not even weakly elementary. Do you guys remember what weakly elementary meant? Weakly elementary meant that there is a maybe infinite set of sentences that weakly elementary meant that there is an infinite or finite, or but just any set, a set of sentences that you can write such that the models in this structure, weakly elementary means that there is a set of sentences which may be infinite, such that the structures in this class are exactly the models of that whole set of sentences. Okay? So in other words, what we are saying here, let's write it down. There is no set gamma of well-formed sentences such that a structure G is going to model gamma if and only if G is a connected graph. Okay, so that's what I say by saying that this class is not weakly elementary. There is no set, so not just no sentence, not even a set of sentences, such that being a model of it is exactly the same as being a connected graph. So how are we going to show this? Well, the proof is going to be by contradiction. So we're going to suppose that such a set gamma of sentences exists, and we are going to prove that we have a contradiction, but showing that if all connected graphs satisfy these the sentences in this gamma, then there must be some disconnected graph that also satisfies it. Okay, so here's what we do. So we're going to extend the language, the vocabulary. So let tau be the vocabulary of graphs, which I guess we just call it E. This is the symbol, but E, binary relation. And then we're going to add to it 2 constant symbols. Okay, let's call it C and D. And then these 2 are going to be, okay. And now we're going to consider the following set. So we're going to let T be the set that contains first all the sentences in gamma, which is the one we are assuming might axiomatize all connected graphs, and a lot of other sentences that we're going to call phi sub n, one for each n in the natural numbers, and where each phi sub n is a well-formed sentence, so WFS, I'm using WFS for well-formed sentence, that says the following. It says, there is no path from C to D of length n. Okay, so phi sub n says it's a sentence that says there is no path from C to D of length n. So let's write it here. So phi sub n is a sentence that exists not, so there doesn't exist x1 up to xn such that C is related to x1 and x1 is related to x2 and x2 is related to x3 and x3 is related to x4 and all the way up to xn is related to D. Okay, so this is saying there is no such sequence x1 up to xn that satisfies this. Okay, so so if gamma was actually the set, was actually axiomatizing the connected graphs, then any model of gamma will be a connected graph. And therefore any model of T will have to be a connected graph too. But then you have to be able to interpret C and D, and if it's connected, that means there is a path between them. And the path between them is going to have some length, 17, 47, 1 million, I don't know, it's going to have some length. And that means it's not going to satisfy the formula phi sub n, whatever the length of that path is, right? So if gamma is actually axiomatizing connected graphs, you can never satisfy these and phi sub n at the same time, because all the phi sub n's at the same time. Because phi sub n says there is no path of length n, and if you put all n's together, it's actually saying there is no path at all between C and D, right? So notice that we couldn't put them all together in one sentence because each sentence here is kind of like getting longer and longer, right? This sentence has a lot of symbols, I don't know, like 4, 5, n plus 3 something symbols. It's a lot of symbols, and it's getting larger and larger with n. So there's no single sentence that does the work of all of them together. We can have to write a different one for each n, but if you put them all together in a set, if you satisfy all these sentences together, it means there is no path at all between C and D. So what we need to show is that this is so if gamma was actually axiomatization for the connected graph, this should not be satisfied, right? They should not be able to get a graph that is connected, but at the same time there is no path between C and D. So the contradiction is going to come because we're going to show that actually T is satisfiable. So how do we show that it's satisfiable? We're going to use compactness. And so that means we let T0 be finite. So that means there is let's call it n0 such that T0 is a subset of gamma union phi sub n for n below n0. Okay, if you have a finite set of T, it has to be a subset of these, and it has to be a finite subset of these two. Like one part is subset of these, one part is subset of these. So finite subset of these means that there is some biggest n that is being used. Let's call that, let's say, n0, if that's the biggest n that is being used. And then we get that the t is contained on that. All right, so the observation is that gamma is, this t0 is satisfiable. How do we show that it set is satisfiable? Well, one way is to explicitly show a model for that set. So what will be the model for this set? So let me just draw here. Essentially, it's going to look like a line, and then in between here we have like more than n0 elements, and we are going to connect them with edges, and then we're going to call this one C and this one D, right? If we need to have a model, we need to have vertices, we need to have edges to interpret this binary relation, and we need to have two elements to interpret this constant. So this is the C, this is the D. If they are far enough, we have a graph that is connected, right? This is connected, so it's going to satisfy gamma, which supposedly is axiomatizing connected graphs. And it's going to satisfy these finitely many things that says there is no path of length less than n0, because the path between them is actually larger than n0, which shows one, what there is no path less than n0, but there is a path. So it's still connected, even though there is no path of length less than n0. Okay, so there is, so every finite set of these is satisfiable by a model like this, right? And the larger the n0, the larger the model we're gonna need. So we're not gonna be able to have a connected graph that satisfies all of these at the same time, of course. So by compactness, T is satisfiable but that's a contradiction because T says what? That it has to be by a connected graph because that's what gamma says, where C and D are disconnected. And that's the contradiction. Okay, so what is it? Let's review the summary of this proof. So we wanted to show that there is no set of sentences, gamma, such that you're a model of it if and only if you're a connected graph. Being a graph is easy. This is the only axiom for being a graph. So the difficult part comes from the connectedness. It cannot be axiomatized. So how do we do it? Well, we assume towards a contradiction that such a gamma exists, and then we got a contradiction at the end. How do we get the contradiction? Well, we extended the vocabulary with two new symbols, C and D, and then we consider this theory, this set of sentences. The set of sentences contain gamma, the one that we are assuming axiomatizes connected graphs, and we added all these sentences that where phi sub n says there is no path from C to D of length n. And then we put them all together, all these sentences together. Okay, so now a model of T will be a connected graph where there is no path at all between C and D. So that cannot happen, right? So this cannot happen. You can have connected graph being connected, but at the same time 2 points being disconnected. So this should have no models at all. So the contradiction is going to come because we're going to show that it should be satisfiable by compactness. How do we show it's satisfiable? Well, every finite subset is satisfiable. How is that? Well, we just take any finite subset and we say if it's finite, then you only use infinitely many of these sentences right here. And if you use finitely many, you can find the model. Let's say you use only the formulas phi sub n for n less than n0, or a subset of those. And it's satisfiable by what? Well, I'll just take this model, so let's say here, it's a line graph. It's a graph where the connections are all in a line, and the C and the D are at the ends, and there is no path between C and D of length less than n0, but still there is a path, so it's a connected graph, and it satisfies there is no path less than n0. So every finite subset is satisfiable. So by compactness, you should get that everything is satisfiable, but that will lead to a contradiction. So there is no such a sentence gap. So there is no first order way, even with infinitely many sentences, but there are no infinitely many first order sentences that can axiomatize connectedness. Okay, we'll see more examples in the next videos.